All right, so this is going to be the last part of unit number 6. We're talking about work and energy, where we focus more on thermal energy and the energy within a substance not necessarily related to its actual movement in the world, but just of the object itself. So that involves thermal energy, the transfer of energy, which is heat, and temperature. And really the big thing about that is how it's transferred, and that is about heat energy, the value that depends on how much energy you'd need to heat something up, to increase its temperature. So that, the amount of energy depends on three things. The mass of the substance, so if you have more mass, it's going to take more energy. And it also depends on the material. If you think about water versus heating up a metal, different amounts of energy, and they'll gain the same amount of energy. They'll gain different temperatures because they don't need as much energy depending on the substance. And the other thing is the actual temperature itself. If you're trying to raise something by a lot, an increase in temperature by a lot, you're going to need to give it more energy. Whereas if you're just trying to change it a little bit, you won't need as much energy. So we give heat energy the symbol Q, lowercase q, with the formula Q equals m for mass C times delta T, where T in this case is temperature. So we have temperature. We have C, the material, which is actually called the specific heat capacity, and that's unique to any material, and that's just information you can get from a table of known values. And mass, and this is in kilograms. Temperature can be in Kelvin or degrees Celsius. It actually doesn't matter which one, which is interesting and unique. And the units, as this is an energy, it is the heat energy, the amount of energy transferred, it is in joules. So the definition of heat energy is the amount of energy required to change the temperature of a given amount of substance. So we're looking at changing the temperature by giving it energy, and that's what this equation tells us, that if we want to change the temperature, we have to either give it energy to increase it or somehow transfer energy away from it to decrease the temperature. So specific heat values, you can see some of them here, where you've got a low of lead. It only takes 130 joules to heat it 1 kilogram up 1 degree, whereas it takes 4,180 joules to increase 1 kilogram of water by 1 degree, which is a very big difference. That actually results in 32 times more energy required to heat up the water, which is a big difference, and that's very important to understand some of the characteristics of water and why we use it to cool things down, and why it doesn't always takes a long time to boil. So what we also want to talk about though is this example. So if we have a cast iron skillet and it's heating up to between these two temperatures, how much heat was transferred? Well, we just write out our givens. We're given kilograms and temperatures. We use the chart above to figure out the specific heat, the value of C for iron, which is 450 joules per kilogram Kelvin. And then we just figure out Q. And remember, our equation for Q is M times C times the change in temperature. And then we just have to plug everything in. 450 joules per kilogram Kelvin times our change in temperature, which we always want to do in final minus initial order. So we have 450 Kelvin minus 295 Kelvin. And to proper sig figs, because in here we see this is only 2 sig figs there, and also 2 sig figs will result from the temperature, we end up with 3.6 times 10 to the 5 joules for the amount of heat that was transferred to this cast iron skillet. So that's how we're going to use the equation. But that energy has to come from something. So energy was transferred to it, and where that came from is something that lost that amount of energy. So that comes to thermal equilibrium. If you left the iron skillet on there long enough, there would be a maximum temperature that it would reach to, because then it would have the same amount of energy as the surface that it's sitting on. So when that happens, we have thermal equilibrium, when the temperatures at the end of a transfer are the same. So the transfer results in the Q of one object gaining and the other one decreasing, but they have to gain and lose the same quantity. So you have QA that's gained energy, and QB has lost that same amount of energy because it was gained by the other object. And to the other characteristics of thermal equilibrium, we have that the final temperatures of both objects or substances you're dealing with, or it can be your system and your surroundings, will be the same. So let's take a look at this in a problem. So we've got our two samples of water, a larger one at 90 degrees Celsius and a smaller one at 22 degrees Celsius. And we're looking for the final temperature when we mix them. Obviously, the temperature is going to go down from the 90 degrees and go up from the 22 degrees because they're going to find a balance point between them. So if your answer doesn't come out something in the middle, then you know you've done something wrong. Because we're dealing with one gaining and one losing, we know we have to start from our point of QA is equal to negative QB. If we don't start there, then we won't be able to have anywhere to go to because we've got two different substances and we don't know the final temperature. So we know that Q, we can expand that equation, and we're using water, so that's why we have C as for water, and our delta T for A, and M, B, C, because they're both water, delta T for B. And again, because they're both water, we can actually cancel out the specific heat values because they're both the same. That's rarely going to be the case, so don't get in the habit of doing that. Now we have to expand our delta so that we have TA prime minus TA, and same for B. But because the final temperatures are going to be the same and I want to solve for one value, instead of writing TB prime, I'll write TA prime minus TB because I know TB prime is the same number as TA prime. Now to isolate, we have to isolate TA prime, which is right now on both sides hidden in brackets. So we have to expand the brackets to first get rid of those. And this will then allow us to manipulate our equation to get our final result. Now, we need to get our TA primes on one side so that we can isolate it and move everything else to the other side. So we have leave this TA prime over here because it's positive, move the other one over, it becomes positive. And then we can move the MATA to the other side, so that becomes positive as well. Now we're just going to factor and then divide by that. So we get TA prime times MA plus MB. And then we can divide by that combined mass value to get our final equation to solve for the final temperature. And when you plug in your numbers, you will get 63 degrees Celsius. So it's important there to realize how we're going about doing that. If your values are hidden in brackets, you need to expand the brackets before you can rearrange. And then you can just slowly work through all things you learned in math class to get to a final answer. That's a thermal equilibrium problem. So we've done a heat energy problem, a thermal equilibrium problem. And the one other type of problem that we might come across is about energy, where if we know how much energy was input and output, we can figure out how efficient it is. So And an example activity that you're going to investigate will be with kettles, the efficiency of a kettle. And the more efficient it is, the more energy you can use that was input, the faster you'll be able to boil the water. And same with cars, the more efficient the engine is, the more it uses the energy in the gasoline. So efficiency is a big topic of research, and it's always important to study how efficient it is. So in this equation is what we would use to calculate it. But that's it for Unit 6 on energy. We just finished up that last one, so that's the end of Unit 6. And as always, physics is awesome.